All right, guys, here we are, chapter 21, number 74. The frequency of a standing wave on a string is F when the string's tension is T sub S. If the tension is changed by a small amount delta Ts without changing the length, show that the frequency changes by an amount delta F such that delta F over F is equal to 1/2 delta Ts over Ts. All right, so it's not exactly clear why we would want to derive such an expression, but part B gives us an idea. It says two identical strings vibrate at 500 hertz when stretched with the same tension. What percentage increase in the tension of one string will cause 5 beats per second when both strings vibrate simultaneously? So here we're looking for a percentage increase in the tension, which would be exactly this delta T over T business here. And it gives it in terms of the change in the frequency over the frequency. So let's first derive this expression for delta F over F, and then in part B we'll apply it to figure out what percentage increase in the tension we need to create this beat pattern. All right, so this expression involves the tension in the string and the frequency. The tension in the string, that shows up in our velocity expression for a wave on a spring. So let's start with the velocity is equal to the wavelength times the frequency, where we get that the frequency is equal to the velocity divided by the wavelength. And we know the velocity for a wave on a string is the square root of the tension over mu, so this is 1 over lambda times the square root of the tension in the string divided by mu, where mu is the linear density. So in this situation, it says that we're changing the tension in such a way that the length doesn't really change. So if the length of the string doesn't change, lambda is not going to change. So we want to find out how changes in the tension affect changes in the frequency. So the way that we're going to do that is by taking the derivative of the frequency with respect to the tension, which is going to be equal to 1 over the derivative with respect to the tension of 1 over lambda times the square root of the tension over mu. Okay, so just to make this clear, I can rewrite this a little bit. The derivative with respect to the tension of 1 over lambda times the square root of mu times the tension to the 1/2 power. All right, so taking the derivative of this with respect to the tension, we have this tension here. So if we take the derivative, we're going to get a 1/2 out in front, and we're going to end up with a minus 1/2 in the exponent. So that tells us that the change in the frequency with respect to the tension is equal to 1 over 2 lambda times the square root of mu times the square root of the tension. Now, this final form of this expression still includes mu, but our expression that we're looking for up here only involves the frequency and does not include mu. So we want to rework this expression a little bit, and in order to do that, I'm going to multiply by a form of 1. So if I take this expression, I multiply by the tension over the square root of the tension here. So now I'm going to rearrange this a little bit. I'm going to take the square root of the tension down here times the square root of the tension over here. That gives us a tension on the bottom, right? And we have the square root of the tension over the square root of mu, and we have a lambda here. So as you may recall, the frequency from this expression up here tells us, this expression tells us the frequency is equal to 1 over lambda times the square root of the tension over mu, and we have a 1 over lambda times the square root of the tension over the square root of mu here. Okay, and then we have left over the square root of the tension times the square root of the tension. So we can rewrite this as 1 over 2 times the tension times the frequency. Once again, this piece right here is what made our frequency. Okay, and we have a tension, square root of tension times the square root of tension. That's tension to the power of 1 that's left over, and we still have our 2. Okay, so we've done this in differential form. What's left is to just say, okay, what if we're taking discrete steps, delta F? So we're going to have delta F divided by F is equal to the change in the tension divided by 2 times that tension, which is exactly the expression that we were looking for up here at the beginning. All right, so for part B, it asks what the percentage increase is when the strings vibrate at 500 hertz and then we hear 6 beats per second. So if we're hearing 6 beats per second, that means, 5 beats per second, then that means that the change in the frequency is 5 hertz. The frequency is given to be 500 hertz, and we want to know what the percentage increase in the tension needs to be. So that's going to be delta T over T. Okay, so solving this expression for delta T over T, we get that the delta Ts over T is equal to 2 times delta F over F, which is equal to 2 times 5 hertz divided by 500 hertz, which is equal to 0.02, or about 2%. More exactly 2%, I should say.